So today continue the previous class, continuation of previous topic discussion, uh, moving charge and magnetism. Okay. So in the previous class here, SI unit of magnetic field is Tesla, and there is a 1 Gauss equal to 10 to the power minus 4 Tesla. Here the field here, that force, magnetic force FB, that is equal to Q, and the magnetic charge, okay, times V cross B. Okay, that's very important. Now there's a vector quantity, magnetic force, and there's a force, a velocity, and that's the magnetic field. And that the velocity is a drift velocity. The velocity now is a drift velocity. Suppose we choose a conductor. Suppose a conductor, like suppose there is a positive charge. Okay, move in that path. Suppose there is a in that path. Okay, and now that velocity in that direction. Okay, so that Vd velocity, and there's a vector. We know that velocity, and there's a charge is suppose plus dq, and that charge is called proton. Suppose consider a proton in that direction. So if the velocity in that direction, so obviously the proton, if I consider that the charge is proton, so current in that direction I. Now there is a where we consider the very small length. Suppose that length is called very small dl. Okay, now choose a magnetic field in that direction B. Okay, so here, so VD drift velocity cross B, that's the angle. That's angle be the theta. The angle be the theta. Very, very important. Now that change that DFB, and the small q of charge, that is a dq. Consider that only a proton dq, that drift velocity cross magnetic field B. Okay, and we know that current I, that is equal to charge by time delta t. Charge flow with respect to time, we get current. So dq equal to I dt, and now replace dq equal to I dt, and vd, the drift velocity, because the proton move in that direction. Okay, if I consider that the electron, so obviously electron opposite direction in that direction. If I consider that's the electron, so in that direction, so opposite direction of that current. Okay, the electron moving opposite direction of the current, and proton, the charged particle, obviously moving in the same direction of current. That's the Vd cross B. Okay, now, okay, dt. Okay, so now I have important is the dl. That's a very small length. That's the length is dl. Now there's the velocity and time. If a velocity multiplied by time, it gets length. Okay, so length by time we get velocity. So velocity into time we get length. So L equal to V times t. Velocity times velocity multiplied by times. Time. So we get a I, and this we get a dl, I dl cross B. Okay, so that's a dfb. Now if I integrate both sides, so dfb integrate dfb, so we get I dl cross B. That's the integration here, obviously, because that's the dl. Okay, and that's the cross product. So dl cross B, That's that if DL cross B, so there is a cross product, and I obviously same path at DL, so that's a B. So okay, so DL cross B, that's very important. We get force. Suppose now elaboration with the help of take an example, a current loop. Example, take an example. There is a current loop. There is a current loop. Suppose there is a loop. There is a current loop. The current direction in the red color represents the current direction. Okay. Now the magnetic field, important. So magnetic field, obviously suppose we choose that in the direction. Suppose that direction, magnetic field B. That's the direction of current I. So here there is a four path at suppose at that point here. So magnetic field in that direction, current in same direction. So you know that force equal to I cross B, like that. Force equal to here I cross B. Okay. So here I cross B. So obviously the IB sine theta. So IB vector cross product sine theta. Here B in that direction. Obviously current obviously same direction. So sine 0. So sine 0 means 0. Sine 0 degree is a 0. So total force here means no force. Here no magnetic force. So FB equal to 0 at that point here. Now choose the magnetic force here. So B in that direction, current in that direction, current in that direction I. So force is I cross B. So I cross B. Okay. So I cross B, that's the clockwise direction. So clockwise direction means the force goes downward vectorically. There is a magnetic force, there is a downward force. Now here choose that here. Calculate magnetic field at this line. This line. So B in that direction, I in that direction. So that's a 180 degree. So I B sine 180 degree. So that's will obviously be the 0. Sine 180 is 0. So 0 times anything you get 0. So there is a no force. Obviously here we get no force. So FB equal to 0 here. Now check magnetic field at that part here. B in that direction. So we choose the universal magnetic field here. Okay. There's a north and there's a bar magnet. There's a south. There's a magnet north to south. So that's the B. I in that direction. So I cross B. So vertically I cross B. So I cross B, that's the anti-clockwise. So that force goes upward direction. Here the force goes, magnetic force is upward direction. Similar at that point here, the same line, obviously current in that direction, magnetic field same direction. So there is a B be the 0. So that's the represent current I. So here we get the two force at that point and here. If there is a force, so there is a rotation. Okay. So if I put a force F, suppose name that line, suppose this line be that A, this line, this length A, the length L, sorry, length A, sorry, here the length A, here the similar, the length A and I, length A, okay, and the current in that direction, that's the current represent I, length A. So here the IDLB, so that means equal to, we get IAB, okay, and so get sine any degree theta, here the sine 90 degree, the sine 90 be the 1, okay, so obviously force be the vector, cross product means there is a vector product, that's why I get equal to IAB sine 90, so that's the angle 90 degree pi by 2, so sine 90 be the 1, cos 0, sine 0 0, sine 90 1. Now there is a rotation, okay, there is a rotation, I will see that very carefully. Rotation means there is a rotation is anti-clockwise rotation, there is a rotation is anti-clockwise. So that's when there is a torque, there is a torque, the tau is a vector product, and that gap, the line join between these 2 points means actually the length for starting from here to ending here, that's the length, that's length, the length represents B. So tau equal to B for R cross F, so you know this B cos F, okay, so actually the axis of rotation here, that's important, so ignore that, that's a B cross F, that's that B means BF, B if we get IAB, the final answer is IA, that's the magnetic field obviously, that's the capital B represent magnetic field, AB at force put here, we get the value IAB, that's the magnetic field, there's the tau, that's the Newton meter. There is a rotation. Now after rotation, now suppose that's that X line and that's the Y line, now change X downward, Y upward direction, look like this. Now this diagram change, okay, that's that anti-clockwise direction, so Y goes upward and X goes downward. Okay, so here is the current direction, obviously, okay. So here the current direction is from starting from X, actually here current direction be the same. Now up to force is here similar condition, if that magnetic field in that direction here B and I goes in that direction, so I cross B, the cross product, so the force goes upward. And similar case, the magnetic field obviously the same direction, that's the B, same direction as that magnetic field, same. So the current direction is in that direction. So the I cross B, that's a clockwise, the force goes, okay, so that the clockwise direction, so force goes downward. Here is the total force, force upward and force downward, it is 0, so no rotation here. But due to inertia, due to anti-clockwise rotation, there's slightly change here, not a 90 degree or there where these are circular loop 90 degree to the magnetic field, a slightly change. Okay, due to that slightly change, I reverse the current direction. Now the second rotation is fully one complete cycle. So Y goes left side and X goes right side. So current direction be the reverse. and again the repetition is processed, and there is an anti-clockwise rotation here. Okay, that's equation. Another way, that's a way from taking NCERT books. And we know that FB, okay, that is magnetic force, or say the Lorentz force, FB, that is Q BD, deep velocity cross B. Okay, and the charge Q, so here that the N, that is Q per volume. Okay, that's the volume, means charge per unit volume, that's N in charge density, charge density, charge per unit volume, charge per unit volume. Okay, where, okay, so that now charge by volume, that is a V, and that a volume is a, suppose there is a conductor of where of length L, and there is a cross section area A. Volume is A times L, so that Q equal to N, volume equal to A L. Okay, now that is important, that the elementary charge obviously present here. Okay, and you see that the external magnetic field, so that a charge carrier means the mobile charge carrier, so that is a NL NAL, and that Q turns here, and that NAL and QVD cross B, important. Okay, there is a Q charge here, the elementary charge, say that. Now the very important, that a current density J, the current density equal to NQVD. So NQVD, we get J. So J A, this A, and now the L. Okay, so that's the L cross B. That's the A force. Now the J times A, J is the current density, current per unit area, I by A. So J times A, we get I. So finally we get the expression is J equal to, J times A equal to I L cross B. That's the F. And now if I put a, suppose that a very small summation put here from all total J I DL cross B. I take a summation here. It is all sum taken here, or say that is a call it integration. If you want to wish to change that summation replaced by the integration, means that is a total sum. Actually, integrate means obviously sum. So there summation means obviously sum. Clear? That's a concept taken from NCERT books. And these two equation same. Okay, that's a very important concept here. Now, next concept we discuss, that motion in a magnetic field. That's the very important. Motion in a magnetic field. In a magnetic field. Suppose we put a positive charge photon here, and there is a magnetic field. Suppose that a magnetic field is present by that dot. That means the V is towards me. Okay, so that very important. There is a velocity. Suppose that the moving is that in that direction. Suppose the velocity here. So means that a plus charge, so current obviously in that direction, I. So B in that direction is towards me. So I cos B. So I cos B. So we get force. That force in that direction. So obviously B, I say that B is point towards me. So force is in that direction. So now that force is in that direction, so means there is a rotation. That photon, a charged particle, move a circular orientation here, direction. I think that's the basic. Now, when that photon move here, positive charge move here, okay, so means there's a direction, rotation direction. So now that photon, the current obviously in that direction, and the velocity tangential v, and that's the magnetic field is towards me. Okay, so I call magnetic field may represent that's the dot towards me. Okay, so I cross the F equal to I cross B. Okay, basically I in that direction. Okay, basically I in same direction. Okay, there is a concept of photon. If photon move that direction, so current obviously follow the same direction. So the I cross B, that means force is towards some point here. Suppose this line is not, suppose replace that, this is center. Okay, now after some rotation that photon goes here. So velocity in that direction, tangential v, basic current in same direction. So that's that magnetic field. There's a towards me. Okay, there's a towards me. Towards me means I in that direction, B I cross B. So I cross B means jump here, force, and the rotation here. And you see that very carefully, there is a force, and this sphere is a circular path, a center seeking force, and this force is called centripetal force. This force is called centripetal force, and the center seeking force, very important. There is a center seeking force now, and the radius is r, the circle of radius is r. That is very important. Okay, so proton plays, if a proton, actually the summary of this concept, if a proton plays a uniform magnetic field, so if a proton plays uniform magnetic field, okay, so there is a force, there is a force, okay, and direction of the force towards the center, and direction actually this direction of the force, towards the center, direction of force towards that center, very important. And depending the direction of the magnetic field, obviously that's the depending the direction of magnetic field. Okay, and that the obviously and current direction okay, so the charge experience that a center seeking force is called centripetal force. This charge experience a force, and this is called centripetal force or center seeking force. So now if I say that a magnetic field, suppose all are the same, but now choose a magnetic field, a uniform magnetic field is suppose cross, yes, towards the board, towards the whiteboard. Now place a charged particle proton, okay, photon in external magnetic field and the velocity in that direction. Suppose there is a velocity, so obviously the current in same direction. So there is a magnetic field cross, so the I cross B. So I cross B, the force is actually that towards the center direction. So now that is a rotation here. There is a rotation, and when that particle goes here, so velocity in that direction, velocity in that direction. Suppose the current of this is same direction, and that's the magnetic field. A cross product here. Here the cross product magnetic field. Okay, that's that I cross B. I cross B. Suppose that the B cross B anticlockwise means goes in that direction force. Similar when a charged particle goes in here. Or here, so the velocity in that direction, because that's the direction B, I obviously same direction. Okay, so there is a force and there is a magnetic cross product. So I cross B, so I cross B, obviously that's at center sequence. That's the center. Clear? The very important direction is matter. Here that is the clockwise direction, that is the anti-clockwise direction. So there is a value depending on the direction of the magnetic field and current direction. That's the key point. Suppose now take a consider like an example. Suppose there is an electron. If you want to, there is an electron. Obviously, okay. The move in that direction. Suppose there is a velocity. So current is obviously opposite direction I. Okay. Now place an external magnetic field here. Similar concept. Suppose there is a cross product magnetic field B. Okay. So magnetic field B, current in that direction. So B in that direction. So I cross B. So I cross B. That means force is the clockwise direction. So I cross B, that's a clockwise direction. So that's why the force goes downward direction. Now that the charged particle electron, this slide not goes their straight path. Now they slide bending in downward direction. There is a bending in downward direction. Okay. Now if I put a, suppose the magnetic field is a dot, suppose in that direction, obviously I in that direction. So the I cross B, that's the anti-clockwise. That's the anti-clockwise. So the force goes upward. If force goes upward, now that suppose that charged particle electron not goes a straight path, just slightly goes upward. The bending upward. This force main cause for bending. This force is main cause for bending downward. This force main cause for bending upward, and that is obviously depending on the magnetic field direction. Clear the concept? Now there is some calculation, but the lecture is too so long here, so I stop the lecture here. Next class we're doing some calculation here. That's very important calculation. Okay. If you have any doubt, okay, in that section, when the motion in magnetic field, when charged particle placed in magnetic field, what will happen actually? That's a very important concept. Okay. If any doubt, always put in comment section. I will try to give the answer. Next class we're doing some calculation here and describe what is cyclotron. Okay, there's a name of instrument, a machine called a cyclotron. That's very important. Okay, so today in the class here, thank you.